Hello everyone, my name is José Manuel Acosta Cuevas. I'm a PhD student from Universidad de Guadalajara and I'm going talking about mapping flow regimen transition for microparticle generation in microfluid device T-Junction. Well, let's start. First of all, microfluid device allow us to manipulate small quantities of liquids for processing, usually in the shape of microparticles. Different fields such as medical, alimentary, and biotechnological have used microfluid device because of stability, control, and time optimization that they achieve. In this study, a T-junction microfluid device was used to generate microparticles and evaluate the effect of injection flow on their size distribution. Hydrogel solution was used as disperse phase and mineral oil has continuous phase. In the first image, we can see a little example of medical file application. Has encapsulate medicine and then release medicine in a system. Then the second image show the structure of a T-junction microfluid device. Now, its application derive two aspects, taking advantage of their size, component, and structure as matrix for material science. On the other hand, they also looking for to improve chemical and biochemical reaction on a micrometric scale for lab-on-a-chip application. Most applications are looking for monodisperse size. Monodisperse size in microparticles is desired for greater control in relays or encapsulation, as well as simplicity in subsequent calculation. Now, the third image shows different applications for microparticles, as drug delivery, cell microcarriers, and 3D scaffold. And the second image shows the monodispersion in the microparticle generate. T-junction microfluid device was designed and fabricated by 3D printing. The diameters used for T-junction were 600 micrometers for the continuous phase and 300 micrometers for the disperse phase. The first image shows the T-junction design and how this was printed using transparent resin to obtain microfluid device. The second image shows the size of microchannel inside the microfluid device. Now, there are different flow regimens, as jetting, dripping, and squishing observed in microfluid systems that generate microparticles. It is necessary to work in a correct regimen to ensure microparticle monodispersion. Because different regimens cause different shapes of microparticles. Different microparticle shapes can imply different size. In the first image, we can see dripping regimen, where the shape of the microparticles are spherical, and then the second image shows a squishing regimen, where the shape of microparticles there is no more spherical, if not has ovoid and larger. Then the image number 3, we can see jetting regimen, and we can see how the disperse phase enlarge into the continuous microchannel to generate microparticles as big as the microchannel allow and spherical shape. The microparticles are obtained in a reservoir with solution to be washed and separated from the continuous phase. The microparticles are then observed under microscope and images are captured. Subsequently, the images are analyzed to obtain their diameters. The image shows the process of how we wash it and we separate to obtain the different image to analyze and show their diameters. Flow rates from 100 microliters to 600 microliters were used for the continuous phase, while flow rates from 0.1 microliters to 1000 microliters were used for the dispersed phase. Different combination of flow radio results in different regimens of microparticle generation. Has shown the table different flow of QC and QD provoke dripping or squishing or even jetting regimen. The second image shows how dripping are made and how squishing or jetting are shown in microscope. However, the transition from one regimen to another does not occur immediately. A transition regimen is required. In this regimen, the flow QD starts to invade the channel to cause the dripping to squishing regimen, while it enlarges in the transition from squishing to jetting. As shown in the previous slide, squishing invades the channel, while jetting enlarges in the continuous channel. Transition occurs above the previous regime, just few values above. As shown the graph, transition regimen has the point line in red and occur above the dripping and the squishing regimen. The flow regimen is shown to be related to capillarity and flow radio. Low values of flow radio and capillarity number tend to dripping generation and conversely. Higher values of flow radio and capillarity number will always cause backflow in the microchannel. In the graph, we can see the radio QD and QC and the capillarity continuous number. If both of them are low values, dripping regimen will be occur. However, if we increase this value, we're going to transition in squishing and then jetting. And if we use higher values of QD and QC, we can go to the backflow. In this backflow, there is no more microparticle generation, because one of the two flows invades all the microchannel of the continuous and the dispersed phase. Avoid the dripping or squishing or jetting generation drop. Finally, the diameter of the microparticle has an inverse relation with the generation frequency. The higher the QC flow, the smaller the microparticle's diameter and the higher the generation frequency. In the other hand, the lower the QD flow, the larger the microparticle's diameter and the lower the generation frequency. This rate is due to the necessary amount of liquid that the dispersed phase flow must supply to reach a large or smaller microparticle diameter. The graph shows diameter from 260 to 460, and we can see the flow rate from 0.02 to 0.1 and frequency from 0 to 35. Now we can see how the smaller diameter show high frequency and higher diameter show low frequency. The frequency in the point 0 is because in 1 second there is no drop generation. However, in this flow radio, in 1/2 second and 2 seconds, we can see a drop generation that have a different frequency belong to 0. In conclusion, the higher continuous capillarity value, the closer the dripping generation is to transition state. Dispersed phase capillarity values below 1 raised to -6 will preserve the dripping regimen. The higher the capillary number for continuous phase, the higher the probability of getting into the squishing region. Higher QD and QC radius will result in jetting and backflow regimens. The higher the microparticle generation frequency, the higher the continuous phase flow and the lower the required dispersed phase flow. As acknowledged, we thank CONACYT for the support and the International Material Research Congress for invitation. Thank you for your attention and invitation.